Okay, let's start. So we're looking at approximation algorithms and looking at this problem set cover. What is this problem is that you are given a universe of n elements. and a collection of subsets of U, let's say S1, S2 up to Sk. And there is some cost function associated with each of these sets. Okay. And what we want is we want some sub collection. S prime is a strict subset of S that covers all the elements of U. Okay. So this problem not just of theoretical interest, has many practical applications too. And one of them comes in the communication industry. Okay. So let's say this universe you can think of as the number of people in a certain locality. Okay. And you want to establish some communication towers. Okay. Those towers will help you send signals to certain subset of the universe, so certain subset of people, right? And there is certain cost associated with establishing those towers, and you want to serve the maximum number of people, but using the minimum cost, right? Because cost is also a important parameter here, and you want to serve as many people as possible. So what is the minimum cost? So where should you establish the towers so that you can maximize the number of people served, but it involves the minimum cost. Okay. So there are two different parameters here. We want to maximize the universe and we want to find the minimum cost of collection. Okay. So that is our problem, which is we want to find the minimum cost of collection that covers all the elements of U. Okay. So here's one example. Let's say our universe consists of 5, 1, 2, 3, 4, 5. And these are our subsets 1, 4, 3, 2, 5, 1, 4, 3, 2. Okay. And these are the costs of these subsets. Say 5, 10, and 3. Okay. This is the blue set S1, red set S2, and green set S3. And we want to pick certain subsets of S1, S2, S3 to cover all these 5 elements. Right? Just one of them doesn't suffice because then some of the elements will be missing. For instance, 2 and 5 will be missing from S1. 1, 3, 4 are missing from S2 and 5 is missing from S3. So you have to pick some 2 of these. And you could pick either S1 union S2, S2 union S3, or S1 union S3. So if you pick S1 union S2, the cost will be 15, 5 plus 10. S2 union S3, the cost will be 30, right? 10 plus 3. And S1 union S3, but then 5 will be missing from that set, right? 5 is not contained in either S1 or S2. So you'll pick the minimum cost such thing. So in this case, it is S2 union S3, and the cost is 30. Okay. So how do you find the minimum cost such selection? And solving this problem is very difficult in general, right? We saw a reduction from vertex cover, so from vertex cover to set cover. So how did we model it? It's think of all the set of edges as the universe, and you want to cover this set of edges, and the individual subsets will be the set of edges which are incident with a particular vertex. Right? So any vertex cover problem, you can model it as a set cover problem. So if set cover were easy, then you could also solve vertex cover easily, but that is, we don't believe that we can solve it easily. Okay? Both these problems are equally hard. Okay. So getting an exact solution is difficult. So we need to consider some kind of restriction. So in this case, we are okay with some approximate solutions, right? So We are not asking for the minimum such collection of subsets, but which are close to the minimum. So we apply this natural strategy here, which is greedy approximations. Okay. We apply this greedy algorithm. And how do we pick greedy set here? So there was one suggestion which said that we just sort the sets according to their cost and then pick the minimum cost of each set. Okay. But that doesn't work because there might be a smaller subset of subsets which possibly doesn't follow the sorted order, but the total cost might be minimum. Right? So just sorting doesn't help. So we need to use a different strategy. And the strategy we applied was this cost effectiveness measure. Okay. We said that the cost effectiveness of a set S is cost of S divided by S by C. Okay. So let's say we have picked certain sets, we have covered certain elements. How do we pick a new set now? Okay. So we'll look at this measure is that ideally it should have the minimum cost and it should cover as many new elements as possible. Okay, so if C is the set of elements which are covered, we want this set S by C to be as large as possible. Because if it was covering the same elements, there is no use of including this new set in our set cover. Right? So that is why we took this ratio, which is we want the cost to be as small as possible, and whatever are the uncovered elements but which are covered by S, that set should be as large as possible. So we took this ratio, cost of S divided by S by C. In fact, you could take any function which is maximizing S minus C and minimizing the cost. Okay. But in this case, this is a very natural thing to do. So because there are two different things involved here. We are minimizing something, we are maximizing something. And in such cases, we normally take the ratio of these. Okay. So for instance, if we have this set S 1, 2, 4, 6, 8, and 2 and 4 are already covered by previously chosen sets. And let's say the cost of including this set S is 12. Okay. So there are three new elements which are being covered by this set S. So the cost effectiveness will be just 12 by 3. Right? Cost divided by set of uncovered elements. Uncovered elements are 1, 6, and 8. Okay. So the cost effectiveness we will denote by alpha, and in this case, alpha is equal to 4. Okay. So this is our algorithm is that initially we said the covered, there are no elements covered because there are no sets being chosen in our set cover. Right? So initially the set of elements which are chosen is empty and there is no set in our set cover. Then we start picking this set which is minimizing this ratio, cost of S divided by S minus C. Okay. And we pick those set S and all the elements in set S are now covered. And again, you find this ratio for every remaining subset, take the minimum among those and update the set of covered elements. Okay. So there was some doubt last time that is this too expensive? It doesn't turn out to be too expensive here because in each step we are adding one subset, right? So the set of subsets is already part of our input. Let's say there are m subsets and you want to cover a universe of n elements, right? So this procedure you will repeat only m many times, right? Because you don't choose the same subset again in your set cover, right? And every time you are minimizing this ratio, finding this ratio is again easy from the input. Right? We look at the set C of covered elements, which is just obtained by taking the union every time and finding the set difference. Okay? All this you can do in polynomial time. So every step of the procedure takes polynomial time, and this procedure is repeated m many times if you have m many subsets. So overall, it's just polynomial time greedy algorithm for approximating the set cover. Okay. Now, once we have done this, we want the total cost of the subsets we have chosen, right? Because we can't just add the cost effectiveness and get the final optimum value, right? Because it will just give summation over all sets in our set cover cost s by s by c. We don't want this s by c, right? We just want the sum of the costs of the subsets which are involved. So how do we do that? That's the main issue. Uh, how do we find the final optimum value? Okay. So for that, what we will define is this notion, which is that for every element in the universe, let's say price, so E is some element in the universe, we set its price to be alpha. Okay. So for every element in the universe, we look at the first set which is covering that element and set the price of this element to be the value of alpha for that set. Okay. Cost effectiveness of that set. Right. So for instance, here we chose this set S in which 2 and 4 were already covered, and it is covering 3 new elements, 1, 6, and 8. Okay. So we'll set price of 1 to be the value of alpha for this set, which is 4. Price of 6 will also be 4. Price of 8 will also be 4. Okay. And then we sum the prices of every element in the universe. So its total sum will be exactly the cost of that subset. Because finally what we want to do is that we want to sum up the costs of all the subsets in our set. Right? So for every element, we look at the first set which is covering that element and look at its cost effectiveness. That will be the price of our element. And finally, we will sum up the prices of all elements. Right? So why did we pick the first set subset is that every element we want to map it to a unique set in our set cover. Right? So you could pick the first, you could pick the last, but first is generally the more convenient one. And we just sum up the prices of all these elements. That will give us the total cost of all the subsets which are involved in our set cover. Okay, so let's look at what our algorithm is. This is greedy set cover. So you are given the universe, you are given this set of subsets, and you are given the cost of each such subset. So C is initially empty, and while we are so initially we haven't picked any subsets in our set cover, so the elements covered are just empty. Okay. And eventually we want to cover the entire universe. Okay. So while C is not equal to universe, we just find the set S whose cost effectiveness, which is just the cost of that subset divided by the number of uncovered elements. Okay, or newly covered elements, as we say, where C is the set of already covered elements and S is our set. Okay, S minus C. So we want this to be minimum, alpha to be minimum. And for each element which are newly covered, which is S minus C, we just set its price to be alpha. And then we have to update the set of covered elements. So the new set C will be C union the set of elements which are contained in S. Okay. And then again, we repeat this. If it is not equal to universe, again pick some new set such that this cost effectiveness is minimum and update the uh, total number of covered elements until we cover all the remaining elements. This is a polynomial time algorithm because every time we are picking a new set in our set cover. So the procedure will repeat only some m times if there are m many sets. And finding this ratio and finding the minimum such ratio, you can do it in whatever log n, whatever is your favorite algorithm for computing the minimum. Okay, so it's a polynomial time, it's a greedy algorithm, and it's also a approximation algorithm. Now we want to analyze how good is this approximation, because it is not clear that this strategy will always give the minimum number of subsets. Right? So how close is it is to the minimum, and generally this analysis of approximation algorithm, that is the more harder part. Right? Designing is not that hard, but analyzing an approximation algorithm requires a bit of technical tools. Okay. Okay. And what we will see is that it is a log n factor approximation algorithm for the set cover problem. Okay. So if the optimal set cover is of size m, we will get some solution in m times log n. Okay, which is still good because generally in this application, this universe is very large, right? So because I gave you that application where you want to establish towers for maximum number of people. Number of people can go in millions in a locality, right? So even if you get some set which is not the minimum number of sets in our set cover, but it's log n times the minimum, it is still a good algorithm. Okay. We don't know any constant factor approximation, unlike the previous cases like vertex cover or TSP, where we got a 2 approximation. Here, the approximation factor is slightly worse. In fact, this problem is very hard to approximate. So, it is difficult in general even to get approximate solutions, and you can show that it is NP complete to approximate such problems, but we won't go into those kind of proofs. They are beyond the scope of this course, and we don't have the time as well to go. Okay, so we'll show that this is a log n factor approximation algorithm for the set problem. So how do we analyze this particular algorithm? Okay, so how do we analyze the approximation method? Okay, so finally what we are doing is we are summing up the prices of all the elements. Okay. So and somehow we want to relate it to the optimal solution. Okay. And so we want to give an upper bound on the sum of the prices of all these elements in terms of the optimum. Right? Yeah, tell me, what is that upper bound? Uh, so what is this quantity upper bounded by? Cost of S divided by S minus. So we want to bring the optimal solution into picture somewhere. Right? Okay, so this is the algorithm. How are we going to analyze the quality of the solutions we are going to get using this algorithm? In what cases can this algorithm not provide the exact solution? Uh, okay. So every time we are picking the set S, which is minimizing this quantity, right? But there might be I mean, analyzing such divisions is in general very hard. So because there might be some things like uh, S minus C doesn't have to be the largest ones, right? So let's say our next set we are picking. Uh, so ideally, if there is some set S which is um, minimizing the cost, where the cost of that subset is minimum, but S minus C is the maximum, right? Then you will always pick that set. But it might be possible that in the remaining subsets, there is lot of overlap with the already chosen elements. Right? So that is a bad choice in that setting. Right? So the optimal thing may not always contain the set S whose cost effectiveness is minimum. Right? Sometimes some set S which is having this value large, but you can choose the remaining sets which don't have much overlap with this particular set. Right? So this is not the optimal one. Uh, so because it's a very uh, complex kind of situation, which set are you going to pick in your optimal set? Okay, there is one more thing, which is if all the elements of S are in C, yeah, S minus C will go to 0. That means cost effectiveness will go to infinite. Yeah, sure. That means there is no use of including this set. And minimum cost effectiveness can be cost divided by uh, number of elements. So you are saying cost of S divided by S. Yeah, but it's okay if it goes to infinity because we don't want to include this set S. If all the elements of set S are already covered, then there is no use of including those. If you are just dividing it by the number of elements, then that thing is not capturing which elements are covered and what is this new set bringing, right? What are the new elements which are being covered? So that is why we don't just define it as cost of S divided by cardinality of S, because we want to see what are the new elements which are being covered by this set. Right? So it is for that reason that we are including S minus C, which are the newly covered elements in this set. Okay. Any other questions regarding this algorithm? Why we are doing what we are doing? And what is the quality of solutions we are producing using this algorithm? Okay, so there is another question. So if cost of S1 is C1 and cost of S2 is C2, then cost of S1 union S2 will be C1 plus C2 um, minus cost of S1 intersection S2. No. So the costs are already given to us. It is part of the input. For every subset, there might be different costs. So it is not necessary that these costs follow this certain pattern here. So what you are saying is the cardinality of S1 union S2. That is some of the cardinalities of S1, S2, and then you minus S1 intersection S2. But the cost function may not always follow this particular pattern. So for instance, let's look here for algorithm. So in fact, yeah, so it doesn't have to be necessary that the cost function. So these costs are absolutely arbitrary. It's not necessary that cost of S1 union S2 will be. S1 union S2 may not even be in my set set of subsets. Right? Yeah. So let's see how do we prove that this is a log n factor approximation algorithm for the set cover problem. Okay, so for what is the final thing which is output by our finally we are returning the picked sets and then summing up all their costs. The way we define the price of every element is that we sum up the prices of every element, and that is the optimal number of optimal cost for us. Okay. So we want certain upper bound on this price of each element. Right? And what is the price of element is that we look at the first set which is covering that particular element. We look at this ratio alpha for that particular set. Okay. So how are we going to upper bound this particular ratio? Okay. So what we'll do is we will number the elements in the order in which they are covered by the algorithm, and you break ties arbitrarily. Right. So the first few elements are the elements of the first subset we are picking. Okay. And then we pick the next elements which are covered, then the next, and so on. Okay. We don't have to worry about how to break ties. Like the first subset will have many elements. So which one should we pick first? You just break them arbitrarily. Okay. So let E1, E2 up to EK be that order. Okay. Or in fact, if we say that our universe has n elements, so this would be E1, E2 up to En. Okay. Now, what we want to show is that for each k in 1 to n, price of Ek will be at most the opt by n minus k plus 1. So opt is the number of subsets in the optimal solution. Okay. And divided by n minus k plus 1. Right. So remember that what was the price of Ek? It is the cost effectiveness, that ratio alpha, which is just the cost of that subset, and it is divided by the set of newly covered elements. Okay. And that we want to claim is that it is at most optimum divided by n minus k plus. So how do we prove this lemma? Okay, this one more question. Yeah, the cost is given to us for every subset of x. Actually, it may not be given for every subset. If it is not given, then you assume that it is infinity. Yeah, but in general, you can assume that the cost is given to you for every subset of S, and you want to pick some subsets so that you can cover all the elements of the universe. Okay, one more question. What is EK? So these are just the elements which are contained in the universe, right? So number the elements in the order in which they are covered by the algorithm. Okay. So E1, E2 up to En, these are the elements in the universe. Okay. And we followed this ordering is that whichever elements are first covered in our chosen subsets, right? they will be ordered first. Okay? And you break ties arbitrarily. And let's look at the kth element in this ordering. That is what we call as EK. Okay. And you want to show this claim is that price of EK is at most optimum by n minus k plus. And this holds for every k from 1 to n. Okay, let's see. So this is the situation which we are having. Let's say this is the optimum set cover. Okay, these are the subsets which are chosen in the optimal set cover. And this is what our algorithm is doing. Okay. So it is covering certain elements, and let's say we know the subsets which are covering the first k elements. Right? That means you know the price of each of these ek, and what we want to show is that it is upper bounded by optimum by n minus k plus 1. Okay. So there could be some k minus 1 subsets before it, right? I'm just saying at most k minus 1 subsets before it, right? Because each subset can cover 2 or maybe 3 or maybe even larger number of elements. But in the worst case, you could have that each subset is covering just one element. In that case, you will have k minus 1, at least k minus 1 elements covered before this element ek. Right? And what we want to say is that in every iteration, the leftover sets in the optimal solution can cover the remaining elements at a cost of at most op. Okay. So let's say we have covered this first k elements, right? So the optimal solution will cover in some different way, and our algo is choosing, it might cover them using some different set of subsets. Okay. So we'll choose, let's say we choose the different set of subsets chosen by our algo, and then cover the remaining elements using the solution given by op. Okay. So the leftover sets in the optimal solution that can always cover the remaining elements. And what is the total cost of these subsets which are chosen by opt? It is at most opt. Right? So it can always cover the remaining elements at a cost of at most opt. Okay. And because we are choosing the minimum value of the ratio, right, which is the cost of that subset divided by the number of newly covered elements. Okay. So greedy algorithm will choose the set where there must be an element with, in fact, price, I should say, with price at most opt by C new, where C new is the newly covered elements, right? Because what will happen here is that if we choose a set where some element has cost more than this opt by C new, then the total cost will be more than the opt, right? So this greedy algorithm, we are always minimizing that ratio. So the minimum must always have cost at most this opt by C new, okay, where C new is the uncovered elements. Okay. And what is the set of uncovered elements? What is the cardinality of the set of uncovered elements? It's just n minus k plus 1, right? Because what has happened here is that we have picked k minus 1 sets and we are choosing the kth set, right? And this k minus 1 sets will cover at least k minus 1 elements. If you assume that each set is just covering one new element every time, then it is covering just k minus 1 elements, and in that case we still need to cover n minus k plus 1 elements. Right? So I hope this is clear. So we have this 20, that price of Ek is at most opt by n minus k plus. And now finally we want to sum up this for all k from 1 to n. Right? So we want to sum up opt by n minus k plus 1 for all k from 1 to n. And that is what we want to bound. From that, we will conclude that it is a log n factor approximation. Or this Hn, if you are familiar with some calculus, this kind of series is called a harmonic series. Okay. So this was the equation we had, is that the total cost is the sum of the prices of every element from I equal to 1 to n. In fact, I should have written k equal to 1 to n and sum of the prices of Ek. Or in fact, this thing should be price of Ei instead of Ek. Okay. And this is upper bounded by opt by n minus I plus 1. Okay. And we are summing it up from I equal to 1 to n. So it turns out to be this summation, which is 1 by n plus 1 by n minus 1, 1 by n minus 2, so on up to 1 times the opt. This is known as a harmonic series, right? There's arithmetic series, geometric series, and similarly, this is the harmonic series, where the inverse of all these are in arithmetic progression. Okay, so you might have seen that. And how do we bound the sum of all these? 1 plus 1 by 2 plus 1 by 3 up to 1 by n. So you just integrate 1 by x dx, right? That will give you an upper bound. And remember your calculus, so 1 by x dx will just be log x, right? So the total sum will be upper bounded by log n times of. So this Hn is approximately equal to O of log. Okay. So many different things come into play here. You have to, because finding the sum is not always very easy. So you have to apply some calculus tricks here, which is, if you want to sum up these things, it is at most the integral of 1 by x dx, right? Which is just turns out to be log. Okay. Okay, any questions on this algorithm or whatever analysis we have done? Okay, there are none. That is good. Okay. So we'll then move on to the next problem, which is a bid packing problem. Okay. Okay. So what's this problem is that you are given n items with sizes a1, a2 up to an. Okay. And each of these ai's are between 0 and 1. So there are some fractions between 0 and 1. And what we want is we want to pack these items into unit size bins. Okay. So there are these bins where each of these bins has size 1. And you want to pack these items into these bins so that the total number of bins used is minimum possible. Okay. So one practical example you can think of it is, let's say you have these n documents which you want to print. And let's say you have only m many printers and you have only, let's say, 30 minutes to print all these documents. So which document you will send to which printer is the same as packing these items into this kind of bins, right? Because each document will have different printing times depending on their size, and you want to print all of them within, let's say, 1 hour. Okay. So you want to run each printer for 1 hour and print all of these documents. Okay, so a bad strategy is we just use one printer, but then you have to wait for one document to get printed before printing the next one. Right, so that is a bad. So it involves some waiting time. If you have multiple printers, you can simultaneously print multiple documents. Right, it's a very interesting problem called the bin packing problem. It is pack the items into unit size bins so that the total number of bins used is minimum possible. Okay. So here's one example. We have all this. Let's say we have these numbers. One of them takes 0.3 time, 0.2, 0.2, 0.2, 0.2, 0.4, and 0.5. And you have to pack them into these bins so that the number of bins is as small as possible. Okay. So each of these bins has size 1, right? And you want to use the minimum number of bins. So here is one solution, which is first you put the job with 0.3, 0.2, 0.2, 0.2. The other bin contains 0.2 and 0.4, and the third bin contains 0.5. Okay. So each of these bins is packed. So if you look at the total sum of the elements which are contained in each bin, it turns out to be less than 1. Okay, so this is a valid packing into bins of size 1, and it requires 3 bins. Okay, you are covering all the elements here. But is this the optimal one? Right? Can you get lesser than 3? So if you sum up all these values, you will see that the total sum will be 2. Right? First here 0.3, 0.5, 0.7, 0.9, 1.1, 1.5, and 2. Right? And we have unit size bins. So natural to assume that you can do it using 2 bins only. You don't need these 3 bins. So here we are not just interested in what is the minimum number of bins. We want to find how to pack these particular elements inside unit size bins. Okay. So here's another packing, which is just using 2 bins. Okay. One of them contains 0.2, 0.3, and 0.5, and the other one contains 0.2, 0.2, 0.3, and 0.4. Right? So you are covering all the elements. One of these contains 0.2, 0.3, and 0.5, and the other are packed in the other. Right? So you can do it only using 2 bins. And in general, this is another example of an NP complete problem. How to pack all these elements using as few bins as possible. Can we relate it to 0-1 knapsack? Yeah. So in fact, what I want to say is that we are not doing the NP completeness proof for this one. But the reduction, how we will prove that it is NP complete, it comes from this knapsack or subsets. Yeah, exactly. That is a good point. That we can indeed relate it to 0-1 knapsack. In fact, you can also give a reduction from this to 0-1 knapsack or subset sum or partitioning problem. Okay, so all these are very difficult problems in general, but it's not possible to find the best packing in polynomial time, or at least we don't know of any approach yet. But again, we want some approximate solutions. Can we give the number of bins to be approximately equal to the minimum number of bins? Okay. So how are we going to pack these elements? Any ideas? How are we going to pack these things? Okay, there is one. What does it mean to pack an item into a bin? No, we just put it into whichever is the empty bin. So packing doesn't have any other meaning. It means that we just put it, if that particular bin is empty, we just put it. So how are we going to put all these items in these bins? And the maximum capacity is its size. Yeah. So we don't want to exceed this. Capacity is only one of each bin. So you don't want to exceed it. So for instance, you take this example, how are you going to put it? Right? So as to get the minimum number of bins. Okay, there is one idea. We can start from largest element and try fitting it into one bin. If it doesn't fit, then in new bin. This way, smaller elements can possibly fill the gap. Yeah, so it's sort of the same idea, but uh, right. So we need to decide which element to put in which bin. And that's the main decision we want to make in this algorithm. Is how do you decide which bin to put the new element? Okay? And these elements are in arbitrary order. So you don't have the largest element first. Of course, you can sort it and pick the largest element and put it in the first bin. Yeah, but in general, this could be any arbitrary order. Aren't all bins equivalent? Yeah, they are all equivalent. Sir, we can choose the item such that the total size is 1 and we put into bin 1. Then we can repeat this procedure and the number of bins used is output. But this is a very hard problem in general. Like how do you choose the items whose total size is 1? Right? So this is a subset sum problem actually. Right? You are given these elements and then you are going to pick those whose total size is 1. So effectively, you need to consider all possible subsets until you find the subset whose total sum will be equal to 1. Right? It might take even exponential time to find those items whose total size is 1. Okay, there is one more thing, which is, yeah, choosing a subset will in general be hard. So yeah, but we are anyways not looking for exact solutions here, so can choose something to minimize the total number of bits. Okay. Okay, so I will give you one algorithm, which is known as the first fit algorithm. So it just places the items in the order in which they arrive. Okay. So I'm not doing any minimum or maximum, like whatever is the maximum, I'll put that first. I'll follow the same order. Okay. So it's a kind of online algorithm where I receive a new element, right? Because in this, the input is not given all at once. I'll just process one input at one time. Okay. So once 0.3 comes, I will decide which bin to put it in. Then when 0.2 comes, I'll again make a decision which bin to put it in, and so on. Right? So these kind of things are called online algorithms, where the entire input is not given to you. Only a small fraction of input is given. Based on that, you have to make decision regarding what will be your output. Okay. So we place items in the order in which they arrive and place the next item into the lowest numbered bin in which it fits. Okay. And if it does not fit into any open bin, then we start a new. Okay. So here, so an example, let's say I had this set S of these sizes, which is 0.4, 0.8, 0.5, and all these values are given to you. And I will follow this algorithm, right? Place the items in the order in which they arrive. Okay. So first what you'll do is you'll put this 0.4 in the first bin. Then you see 0.8 is too large. So you have to put it in the next bin, 0.8. 0.5 can fit into the first bin. So you'll put it here. Then 0.1, again, it can fit in the first bin, right? 0.7 is too large. It can't fit here. It can't fit here. So you'll put it in the next bin. Okay. And you keep on doing this and get some bin package. Okay. So in this case, you get 5 bins in which you can pack all the items. Okay. Right. This is the first fit algorithm, which is that we pick the lowest bin in which that particular item fits. Okay, I'll stop here. We will analyze what ratio approximation it is. Is it? Okay. The next class. Any questions about this algorithm? Yeah, there is one question. 2 8. Okay, you are giving a smaller this thing. This might fit in 4 bits. Yeah, it's very much possible. We are just giving an approximation algorithm here. So you might find some smaller number of bits, right? But uh, the main point here is that we want to find an algorithm which can uh, find the minimum number of close to the minimum number of bits. Right? Now, of course, we have the entire thing, so you can find smaller number of things, and largest element first will be more efficient, I think. Okay. Yeah, maybe. Let's discuss it in the next class. Okay, then I'll stop this meeting now. Meet on stage.